is an MIT student in machine learning, and my son. And also my nephew, Yiwei Lu, who is a PhD student in machine learning at University of Michigan. Actually, they offered a machine learning course in AOS Summer Camp 2023. And this is the first time I'm learning machine learning. And I sit down in their class and I suddenly find, oh, it's so cool, it's everything in mathematics. So I said, cool, I definitely want to step into that area. So their class actually introduced me a fascinating world of machine learning. And since then, I applied this tool in finance research and recently achieved a very positive result. This talk is inspired by their class. Actually, some of the slides have been adapted directly from their class material. So that's why I thank them. And in case I didn't explain something clear, my son happened to be here, spring break, so he can correct me immediately. Okay, next slide, please. So first of all, we would like to talk about machine. So when you talk about human language, how does it connect to number? Because machine only understand number, machine does not understand English word. So machine actually connecting to number by vector. So what does it mean vector? I just give intuitive meaning. Let's assume in vector all starting from origin. In fact, vector doesn't have to be starting from origin. Then it has ending points in the space. So you can think about the ending point as the vector, but strictly speaking, it's wrong. Vector is not a point, but if your initial point is fixed, then ending points and a vector are one corresponding. So this is a 2D dimensional picture. So when you look at why it's so powerful to represent English word by vector, because there is a reason. When you look at man and a king, and you think about women and queen, and look at vector, the difference are same because you really think about how far away men away from king, or away from the royalty. And it's same as women away from queen. So the difference is the royalty direction. And you talk about men different from women, and that's the gender. And also king differ by queen, that's the gender. So when you think about English word, oh, now you can throw the English word into space. And they are all points. I already said if we're assuming the initial points are 0, then it's vector. We say vector, but it's really points, all the points in the space. But how many dimensions the space? Look at this picture. This is 2 dimension. It already show you some feature. But in fact, GPT-2, the dimension is 768. And GPT-3 or GPT-4, GPT-01, the dimension will be 12,000, blah, 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 blah. I don't exactly remember the number. So it's highly dimensional space dot. So when you think about dimensional vector, next slide. So how did you represent the word? Every English word can be represented by vector. And also sub-word can be represented by vector. Sometimes people like English number, alphabetical number represented by a vector. And usually in machine learning, this vector has a name called token. Next slide. So first of all, we understand how our English language can change to vector. Now everything is number. Then the next thing is how picture can change to be number. As long as everything is number, it's good. So picture really represented by pixel. So basically you cut this picture into little square. Once you cut tiny enough, each square only contains 1 color. So if it's 1 color, I can represent by 1 number. And I'm using black, white as an example. This picture is colorful. Then that would be complicated. There are 3 channels, but I don't want to go that deep. But let's just think about this as white, black color. So basically each pixel, either black dot, or white dot or gray dot, and how grayish is in the middle. And we represent 0 as black and 255 as white. So your 200 is more near white side, so it's bright gray. And 2 possibly is, no, not 2, 100 possibly is black gray, okay? So basically every picture you can turn into a matrix. So what's the difference between vector and matrix? Vector, basically, I said, you can imagine it as a point in the coordinate system. So it's a list of number, 3, 5, 4, da, 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 da. It's a list, right? And the matrix is also sort of list, but it has column and row. So you list a number, pixel number like 2, 3, 4, 5, that one row finished, then next row. So matrix is a rectangular shape number. So this is all represented by number. Next slides. So in fact, modern days, we don't cut into one little piece by pixel. This cutting pixel, the numbers of data points is so much. Actually, the modern machine learning powerful tool is called the transformer. When they handle vision, they actually cut into patch. So they are cutting to this amount. And you, by this amount, to represent this patch by a vector. Okay? So basically, next slide. Basically, we're not good. You know, picture is number, language is number, right? Now we can play with number. So basically, two types of number. Either the number is vector or matrix. I would like to talk about model, machine learning model. In fact, machine learning model is deeply rooted by the simple linear regression model. I don't know how many of you have heard simple linear regression. Could you raise a hand? I just want to know how many of you have heard of it. The simple linear regression. Or if you have never heard it, don't worry, I will tell you. So at least y equal to mx plus b is a represent a line in the 2D space, okay, a line. M is called the slope, and b is called the y-intercept. So for example, y equal to 2x plus 1 is a line. And y, I draw a couple lines for you. So this is y equal to x plus 2, and that's y equal to x. That's y equal to negative, oh no, not negative, y equal to negative 5 plus x, okay? So these are all lines, okay? So I would like to compare simple linear regression. First, we try to understand simple linear regression. Can we go to that web link? Because that's so important. Possibly we need a copy paste.
Just 1 second, sorry.
Yeah, it's not a live link. I don't know why it's not a live link.
No, it is. It's on my screen, not over there.
Oh.
Where is it? It's black here as well. Not this one.
Go Chrome. I prefer
Firefox.
Firefox?
Yeah.
Oh,
Yeah,
this one, right?
Firefox. Yeah.
Okay.
Okay. So while you see many dots on the plane, so you say, oh, what good thing of modeling? Why is modeling is good? So modeling is once you have a line there, I clearly know any x value, what's the corresponding y value. So it's really good. How do I predict a line? Could you check mark the first box? So you, ideally speaking, you say in the middle will be good by your eye. But in mathematics, we never do by eye. We want to do mathematics. What do I mean good? Good means, could you click the second thing? Yeah, good means the distance square sum to be smallest. Why? First several English words going to you, maybe you feel overwhelmed, I will tell you. So we want to near to all points, right? We want to near to all points. That's called fair. If I'm very close to this point, it's cool, but I'm far away from other point, that's bad. So you need adding them together to overall loss, right? To be small. But also another thing we need to think about, why do we square it? There is a reason, because we don't want positive error cancelled with negative error, saying no error. There is a famous statistic joke, put your head into oven and put your feet into refrigerator, so your average temperature is normal. So basically just saying the positive error cancelled with negative error was pretty bad. So how do we avoid this? In linear regression case, we make square. So basically, how do we know a line is good or bad? We basically say this distance squared, it's just area. And this distance squared, just area. We want all area total sum together to be smallest. And this is loss function. We want the loss to be minimized. Okay, check mark the third thing. And show the sum. This sum is a line. Now I want to adjust the M and B. You can adjust M and B. Yeah, look. Oh, this M is bad. So see, some loss, you want the red line as small as possible, okay? You keep on adjust M, keep on adjust B, then until your red line hits the minimum. Then you say, cool, that's the best line. Did I make that clear? So then check mark the last one. So that's the best line. If you adjust it towards this best line, 0.42.
0.42.
Yeah, maybe not 42.
They don't enable that.
Yeah, 4.5. Then 5.04. Yeah.
This one?
Yeah.
And B?
Yeah, be 5.4.
It's supposed to be.
Yeah, well, close enough. 5.5.
Okay.
5.
So,
Okay, good enough, good enough.
sorry,
Look.
I'm not good at trying.
Yeah. But anyway, it's good enough. Look, what's the total error? 10 point something. A moment ago, clearly 50. So this is machine learning. Okay, basically the simplest machine learning idea. Basically, you have data points, right? Then you want to adjust your M and B. In machine learning, we call parameter. You try to adjust the parameter until you get the smallest error. Basically, this line close to everybody in the cumulative sense. Okay? So that's machine learning. Okay?
And there's another reason for using squares is to penalize outliers.
Oh, penalize outlier. Daniel specs.
So like if it's super far away, then your error is if like there's one point that's far away, it's going to penalize that point because the square is going to be very big.
Very good, very good. So this is linear regression. So we want to minimize mean square.
Like otherwise you could just use absolute value. In that
Yeah,
way.
sure. So we want to minimize mean square error, which is the average square of the vertical distance of every point away from the line. Okay, next slide. So now I talk about machine learning compare with linear regression, because I teach linear regression a lot, and I didn't teach machine learning, so I thought it's a very good parallel idea. So when you look at linear regression, a moment ago there are only 5 points. But in real life, you don't want 5 points, because 5 people, you can make any conclusion, right? That must be hundreds of points. Then you want a line in the middle, kind of close to all the points in the sense. So I want to compare machine learning with this model. So in linear regression, y, what is y? Y is the y coordinate. So for example, this one's y coordinate is 15, that's y. Okay, every single point has an x, has a y. And be very careful. So for example, this x-axis represents TV. This y-axis represents sales. Basically, x-axis is TV advertisement. Y-axis is the sales. So as long as you do more TV advertisement, your sales will grow up. So usually, why do we do linear regression model? Because we want to do prediction. We want to say, what if $100 spent on TV? What's the corresponding predict value? It's here. So the corresponding value is here. Then anything on the blue line is the predicted value. And anything, the true dot, is the true value. So you really measure the true value differ away from the predicted value. That's linear regression. So in linear regression, y is called observed value. And y in machine learning, y is called label. So in machine learning, we also have a y, correct answer. It's called a label. And also called ground truth. In linear regression, we minimize the sum of square error. So statistic course is important. In machine learning, we minimize L2 loss function or cross entropy loss. You may say, oh, Qing, what is cross entropy loss? I won't go into detail, but I want to intuitively tell you what's cross entropy loss. So simple linear regression predicts an exact y value, right? But machine learning usually predict a lot of time, it predicts a class. So I give machine a picture. It will tell me it's a dog. It not tell me 5.4. If I give machine a picture, it's 5.4, then I don't know what it is, right? So machine will tell me it's a dog. Then I give another picture. The machine will spell cat. So the Y label in machine learning, a lot of cases, it is categorical variable. What's the difference between categorical variable and quantitative variable? Quantitative variable is name, is number. Okay, categorical variable is class. Male, female, categorical variable, cat, dog, tiger, all categorical variable. So in machine learning, a lot of cases do categorical variable. The categorical variable you cannot measure. You can measure the distance, but they usually measure the probability thing. It's really, it's called a cross entropy loss. I don't want to go that detail, but still, it's a distance, sort of distance. I put quotation mark. It's the distance away from true value and predicted value. Okay. So that's the difference. Okay, linear regression minimizes the sum square difference between the predicted value and observed value. Machine learning minimizes the loss function on the predicted value and ground truth. Ground truth is the observed y. Okay? Yes.
Sorry, just a question. Is the cross entropy loss is always a percentage?
No, it's not percentage. It's a probability. It's a
Cross entropy loss is a number.
It's a number.
It's a number based on like the model predicts probabilities for each category, and then the cross entropy loss detects how much it matches the ground truth.
Yeah.
The correct answer.
Yeah, correct.
The correct answer is just like 100% cap, for example.
Right.
So a 98% cap would be a low loss, while like a 2% cap would be high loss.
So the number does it reproduce?
Oh, I was saying next slide.
Sure.
Yeah, sorry.
All right.
Next slide saying it. So go a little bit down. Is this the end of slide?
Yeah.
Oh, okay. I didn't say that. Okay. So basically, I'm saying in linear regression, y is a number, right?
Mm-hmm.
In machine learning, y usually is not a number. Y usually be a category. However, the predicted y is a distribution. What do I mean distribution? So true, you are saying, because if you want to categorize cat, fish, dog, then your output is not cat, fish, dog. Your output is 0.8 cat, 0.1 fish, 0.1 dog. Then your label is cat. Your label cannot be probability. If it's a cat, it's a cat. Label is ground truth, it's observed value. So basically, label is 1 and 0, 0. That truly represent a cat, okay? A cat. So it's kind of measure these two distance. So because one of them is a vector of probability, and the other is one value, all other 0. You cannot measure the distance like L2 loss. You have to measure specific probability weighted sum kind of.
Okay, probability here. If that means the machine matching that much of the category or
No, the model just predicts values for each category.
Right.
So it just thinks there's an 80% chance it's a cat, a 10% chance it's a fish, and a 10% chance it's a dog. So that's a single output from a single image.
Okay.
And that's what just the model outputs.
Okay.
So model never tell you it's a cat.
Yeah.
Model only tell you the
How much
probability
probability?
distribution of all possibilities. Then you usually pick the highest probability. Say, oh, since this is much higher, so I
So
should
my
go.
question is that possibility means, does that means like 80% true it is a,
Yeah, cat.
or 80% of the image is a cat?
No,
No,
no.
it's 80% chance that the
This-
model, like the model has 80% confidence that the whole thing is a cat.
Yeah, your picture input, one
Yeah,
input,
there's
not a
no-
whole
yeah.
input, one input.
But that number has some statistic meaning? I mean,
Technically, not really. It's
Right,
just
right, that's what I mean.
there's no actual meaning because the model's always going to predict cat if it thinks it's 80% chance it's cat.
Yeah,
So
model is
there's not actually a meaning to the 80%. The 80% is just a number used for the loss because if the model is more confident, it can predict like 98%, which in that case it's more confident and that means it's better because then because sometimes instead of 80%, maybe it's 51% cat and 49% dog. Then if we change the image a bit, then it becomes maybe 49% cat and 51% dog, which would change the label. That's why we care about the probability being high.
okay. So what if it's quite low, like 50%, 50 to 50, let's say?
Now your model
Then
is
you need to do another.
Yeah,
another
that
one.
means your
Now,
model
if
is
it's 50, I mean, generally it's not going to be 50-50 because it's real numbers, so it's
Right.
astronomically low. And if it really is, it just chooses one.
Yeah. So anyway, so you are talking about in statistical world.
Sure.
So you are not talking about one picture, it's correct or not. You are talking about millions of pictures.
Yeah.
A millions picture, if there is one or two picture with 50, 149, you're fine. As long as your majority picture very clearly,
Yeah.
correctly labeled, then your model is done. Yeah.
It's a little bit confusing to me, so I just want to have some clarification. So, to me, everything is deterministic. You have a,
No, it's not deterministic. It's
just let me
totally.
finish my question first.
Yeah, yeah.
So, I have a picture, and I have a model.
Mhm.
So, the model has the same set of parameters in it. The calculation will run through every time you input this picture. It's the same calculation. So there is no statistical process in this calculation.
Yeah.
So it's
Yeah.
kind of
Yeah, it's deterministic.
Yeah.
So that's deterministic.
Yeah.
So if I input the same picture and run the calculation, every time I will get 80% cat.
Yeah.
10%
Yeah.
cat.
Yeah, and every time
That's
it'll take
deterministic.
Yeah,
But
yeah.
the result is seemingly a statistical thing, but it's a statistical in a different meaning.
Yeah, it's just
Yeah.
like the point, linear regression. If you give one x, it's always predicted a single y. Statistics in the sense of you look at all inputs together, it has a distribution. A single point, you always have one prediction variable.
Yeah. So
Yeah, this one just predict that. You do this 1 million times as long
But
as
I think what the 80% actually has technically no actual statistical significance. It doesn't say 80% of anything.
Yeah.
So-
Yeah, that was the question.
Yeah,
that was
that's
the
right.
question. What
80% is
that
just a value that shows the model's like confidence.
Yeah,
So like
yeah.
80% is greater. Like 80% means like, for example, it's more confident than if it were to say be 60%.
Yeah, that's
It
right.
doesn't actually mean it's like an 80%.
Yeah,
value.
no, there is no random variables to make it 80%. It's just the total value is give you is symbolically represent. That's more likely happen. So also the linear regression model expressed as y equal to mx plus b. While machine learning contain many parameters, often contain 100 billions of parameters. They combine both linear component and nonlinear component. And in linear regression, we solve for regression coefficients, m and b. And in machine learning, we call training. So training basically is software. So software defined. And in regression, y is a number. In most machine learning, y could be a number. Most likely, it's the category. And the y, predicted y, is a distribution of category.
Excuse me. If the cat is 0.8, okay, would it use that 0.8 for the next image you give to the cat?
No. Next image, you put all images together, try to adjust the parameter. Let's always think about.
It's just there's a model, and then the image goes through one image goes through the model and gets those probabilities. Another image goes through the model and gets like another set of
But
probabilities.
it doesn't use this for the future data set.
Yeah.
So let's look at the linear regression. We still want to understand linear regression because it's same. Like this point predicted here, right? Next point you predict here. In the process, all data are useful. Cooking, right? Once it finished cooking, we said it's finished training. If it's finished training, just like linear regression, m and b are fixed. Now I'm fixed m, fixed b. I'm finished training. Now you give me an m, you give me an x, like 50. I plug in. There is only one y. There is no randomness. And if you give me 100, I plug in. It's another number. It's totally, not 50 plug in. So think about machine learning same way. So just the machine was complicated. You have a bunch of data sets. Then it began cooking. Okay, I will talk about cooking later. It began cooking until it's cooking. Finished cooking, all parameter frozen. Then became next stage we call inference stage. It's called prediction stage. Prediction, one picture you go in, there is one number. You learn second time, it's the same number, nothing changed. Then you get another picture, the totally different number. All the number together, you can talk about distribution because it is probability meaning. A single one, there's no distribution. It's just a number. It's just one output. This was called predicted value. Usually we don't call it random variable, it's predicted value, okay? But all predicted value together, it's a random variable.
So the more data you have, the closer your predicted value close to the truth.
Yeah. Generally speaking, yes or no, but not necessarily, because depending on also that's another question. Depending on your quality of data. So I always want to use linear regression to do it. Okay, I give you a linear regression to explain all the examples. So you said more data good. Okay, I have 1 million data here. Okay, then another few data there. So really you don't know. The line is this way or the line is that way. You don't know. If I only have 4 data points here, 1 million data points there, you keep on adding 1 million data points, it doesn't change. So also depend on your data. It also depend on your data. Of course, you generally speaking, you say this one compare with this one. Of course, more data better. But this one compare with this 1 million dots all coincide together, one point. There's no difference. Did I make that clear? So it's also depend on data always. So not always all better data will give you better. More data give you better. Okay, next slide. So now I would like to let you familiar terminology. From now on, X, we can think of X as image. Okay, just think about X as an image. Basically, image you can transfer to number to be a matrix. A matrix, you can flatten it. What do I mean flatten? I can make, first row finished, and then second row, third row, and make it a vector. So now look at this matrix, 3 by 3 matrix. I can flatten into 1, 2, 3, 6, 7, 8, 9, 4, 5. So basically it's all vector, okay? Vector is the input. Vector is the input. And the Y is the label, ground truth. Okay, let's assume it easy. We do classification, so dot, okay? Then the data set always like matrix 1, represent picture 1, and label 1, dog. Matrix 2, label 2, cat. Matrix n, label n, so many. So theoretically speaking, you need even balanced picture will be better. So like if you have 1 million animals there, if you have 10 categories, possibly 0.1 million cat, 0.1 million dog, 0.1 million, it will be better. That kind of scenario won't happen. Like 99% of data is all cat. Then you have 10 dog, 10 tiger, 10, whatever. Then possibly the model will predict it's all cat. Okay, so that's the issue. So anyway, classification problem really is give me a new image, basically new matrix, and tell me what's the label. What is it? So output, input is a vector. Output is also a vector. Output is probability of cat probability. It's strictly speaking, it's not probability, but we kind of thinking it as a probability. Okay, because why we say it's probability? Because totally it's 100% of chance. It's just add up to be 1. Okay, so that's why we say probability. But truly, yes, this predicted value once you plug in, it's a deterministic number. It's not really kind of thing. Yeah. Okay, next slide. So our job is find parameter. So do a prediction, which is plug in the model. So after you got parameter, frozen it, then the rest of them is prediction, just like linear regression. You throw number in, you get output. You throw number in, you get output. The output is called inference. Okay, so we separate training with inference. Training means you keep on training the weight until you cook in the model. Your model done, training done just means all your parameter was fixed. Okay, yeah, that is the prediction.
Question. So all prediction is based on linear regression? Or
No, not linear, not linear. Much more.
Not linear, right? You can do the high order.
Yeah, I will discuss not totally non-linear. If it's linear, then it's not linear. All word is highly non-linear. Now I would like to dig more on training. From now on, possibly 5 minutes. If you don't have calculus background, you can close your eye, don't worry, and do whatever. But if I lost you, absolutely fine. I don't care how many of you I didn't lose. I just want to go as quick as possible. Okay, begin of my journey of training. Okay, so training basically a lot of calculus there. Okay, so let's still go back to linear regression. What is linear regression? Linear regression, x is the x-coordinate of single point. Why you have xi? Because there are many points. Yi is the y-coordinate, and you want to predict slope and intercepts. Okay? Machine learning is similar. This is cross-entropy formula. Okay? Sorry, not this one. This is cross-entropy formula.
Okay.
Y is the true label, and y hat is the predicted. Okay, Y is the true guy, Y hat is the predicted, okay, the predicted. So this is called cross-entropy loss. When you look at this formula, you say, no, this formula is nothing worse than linear regression. No, it's much worse. Why it's much worse? Because Y hat is a very complicated model cooked out highly nonlinear. So it's a very complicated function. Okay, you can imagine y hat is a very complicated function. Okay, this is a very complicated function. So this formula is much more complicated than the previous formula. So sometimes we don't even bother to write down cross-entropy loss. We just write down L. L stands for loss. And f theta is a very complicated function. You throw xi in and get yi, basically very complicated yi. And all theta are the parameter there. Changing theta, your final answer will change, okay? So this is the function we call loss function or we call target function. Okay, next slide. This is ChatGPT's target function. So there is a lot of problems, not ChatGPT, I'm sorry. DeepSeek. This is DeepSeek's target function. Actually, the tool they use is reinforcement learning. And they use expect value. This is purely probability phenomenon. Or there's a probability distribution, but I don't want to go that deep. Next slide. So how to train the model? So basically, now training the model becomes the optimization question. As I said, overall loss as minimum as possible. So it's a function calculate optimization. So in calculus, we learned set partial derivative equal to 0. Then you calculate optimization or derivative equal to 0. That's a very easy calculus question. However, look at this f. This is highly nonlinear. Then even do partial derivative. So hard, plus partial derivative set equal to 0. It's basically an equation. And this kind of equation totally cannot be solved. So that's why in the older days in machine learning began, neural network idea appeared a long time ago. Why there is no progress? Because people cannot solve this optimization problem efficiently. Now
also, it might not, like, sometimes partial derivative equal to 0 might not be, like, sufficient because
Yeah,
there's, like,
because-
non-differentiable.
Yeah, there's non-differentiable, there is local, I'm very familiar with that, but I don't want to go that. And there's a local minimum, global minimum, no, this is too far. This is all math region, I don't want to go that deep. You are absolutely right, but no need this kind of correction. Mathematics, I'm so good. I have PhD in mathematics. I just don't want to cover, that's too much, okay. Yeah, the next thing. So let's talk about derivative equal to 0. So how did you make derivative equal to 0? Find the minimum points. You say, aha, so easy. My eye sees this is the minimum points. Wait a second. There's no eye. There is no picture. I just gave you an arbitrary function. How did you get minimum points? So in the older days, if the function itself is so simple, take derivative, set it equal to 0. Of course, mathematically, you also need to check local minimum, local max. I don't want to go that. Okay, wave our heads just of derivative roots. Derivative roots are candidate. Okay, sometimes non-differentiable. Then you need to handle it. That's too far away. But anyway, you distract me. This one distracted me too far away. Okay, anyway, so how do I do in a complicated equation? Basically, people doing that way. Pick an initial value, arbitrary. There is mathematics, a whole region of talking about what initial value are good. I don't want to take that direction either. So pick an initial value. I close my eye, I pick here the initial value. Then I calculate the slope of this line. This line has a name called the tangent line. Tangent line slope is just derivative, so you can calculate the derivative. Then if the derivative is positive, you try to move to the left. How did you move to the left? You minus. Your original theta is here. You subtract, you move to the left. Then you move to the left, there is speed. You can move very quick, very far away. Then boom, you miss the minimum. And then you suddenly become negative slope. That's not good. So this is called the learning rate. So you want to properly choose learning rate to move properly. Like this one, you move first step, second step, third step, fourth step, fifth step, sixth step. You move then until you hit the minimum. Until you find your new theta, the derivative equal to 0. Then haha, you get minimum. But there is an issue about local minimum or absolute minimum. I don't want to go that far. Okay. Yeah, this is one dimension. Remember? Machine learning is multi-dimensional. Yeah, next slide. So this picture I steal from online, Daniel's class online notes, not Daniel's notes, they're not allowed to release, but I found a free version online, so I'm allowed to use it. So they draw a very beautiful picture. I said, why I draw it again? I use it. So basically, what do? They want to minimize this loss. okay, this distance away from predicted and true value. So this loss, they want to minimize it, then they do derivative with respect to theta. With respect to theta. Then this derivative is not a single number anymore, it's a direction. So it tells you the steepest direction. So for example, you're on the top of a mountain. You want to go valley, you can go around, or you can directly go the steepest direction. So basically gradient is the steepest direction you're going to slide. That's where you're going to skiing. That's the funnest part, going the steepest. So basically, you are going to the steepest, and you want to go the negative direction, and that's the learning rate too. So basically, you got the next theta. So you truly, gradually, get the minimum. But there is a local minimum, global minimum. I wave my hands, just minimum. Okay? Yeah. Anyway. So, starting even harder. Now go back to your question. Machine learning model, not only nonlinear, it's actually highly nonlinear. How do they do it? They actually build up by layer. So like first layer is linear. When linear in mathematics, usually you multiplication by a matrix. So a vector, if a vector you multiply by a matrix, that gives you a new vector. But that's still linear because matrix multiplication is linear. Then you usually apply a highly nonlinear function called activation function. Then apply activation function, then do another linear matrix multiplication, then activation function, then linear, then activate. So totally it could be many layers, even hundreds, thousands of layers. So it's make the function totally linear. Not only nonlinear, sometimes indeed there is a theorem. That part I can say. In mathematics, any function can be, it's the limit, can be approximated by this kind of thing. As long as you contain enough layer, you can approximate any function as any accuracy you want. Okay? That's very amazing. Like I have a function, I can use many layers to approximate. Maybe after that. Usually if you do approximation, they usually generate like the trapezoid shape. The trapezoid shape adding together can generate the shape. Okay? So this is called backpropagation. So basically you have many layers. So whenever you do partial derivative, in fact you need each layer partial derivative. This partial derivative is this partial is this partial is this, this partial is this. So it's product together. So this is the chain rule. So it's the product of partial derivative. So that's why it's called backpropagation. Backpropagation, you need one forward process. You first import the initial x. You always, oh, by the way, I need to say, so any model, theoretically speaking, you always have a starting point because we cannot solve equation anymore. So we have a starting point. Usually, if nothing existed, you just make starting point totally random. I go back to linear regression again. Or linear regression is totally the same idea. So I want to solve M and B. Of course, there is closed form solution existing. I apply formula, M boom, come out, B come out. But remember a moment ago what I want you to do. I want you to arbitrarily try M1 and 2. Then you find the one line. Ooh, you find the red line, the total error is very large. You say, how about let me adjust this a little bit, go down to 0.8, and to see if it's better. So this is really gradient descent idea. You keep on adjusting your parameter until you hit the minimum guide. So machine learning actually doing the same way. So you need to have an initial value to adjust, okay? So you first give an arbitrary weight. You want, now if you have some experience, you want to give good weight. But if you have nothing there, you just arbitrarily using random generator to generate the weight, all the parameter. Then once you have all the parameter, you can go forward the process. Boom, get one y value. Are you with me? Then begin to changing theta 1 a little bit to see what's y changing. Not y, the L, the loss change. Then it's changing L over changing theta. So that's the gradient idea. Okay? So basically you keep on doing gradient descent. So all the changing is based by chain rule. And they can save the machine backward because if you calculate later layer first, you can save data. And then the later layers data can be used in the next layer. And next layer. So they all.
Will that be a manual work?
No, it's all.
Each iteration.
And then you did the homework of backward propagation, right?
Yeah.
How many days did you spend on just doing this program?
This is like, I don't know, it's like a few hours.
A few hours. Yeah, you have to.
I have to kind of mathematically do it. I have to use linear algebra and calculus, and basically in my brain or on paper or something, I have to actually calculate the thing.
Right.
So there's no like, I mean, there is a.
But you have to check the result, right? You have to check every iteration the result, if the result is better or not.
Well, no, like for like backpropagation, for like just linear, if we're just doing like linear layers and then nonlinear layers, there's several nonlinear layers. Like there's this thing called ReLU, there's this thing called sigmoid. These are all functions that we know about, so we can kind of mathematically actually just calculate the gradient.
Yeah, that kind of non-linear function, the derivative calculation even easier. You can calculate it. So then you can multiply them
And then
together.
there's the chain rule, but we have to actually program that. Like the people who made PyTorch had to program that manually.
But if you use it, you don't need to worry about it.
Sure,
You can
that's
call.
to the wondering.
Yeah. You don't need to worry. No, end of journey. So now everybody need to wake up to see the next one. Yeah, all this is totally mathematical. Then if you're sleeping, that's fine. But from next page on, you need to wake up, okay? So I summarize. Everybody need to hear my summarize. Giving input information, usually many vector. Picture is vector, language is vector. And design model with varied parameter, just like you remember the basic model M and B. There are a lot of M, a lot of B, and nonlinear, okay, basically. And then get a predict Y. Generally speaking, in linear regression, predict Y, just literally plug any X in, you get predict Y. But machine learning, you plug in multi-layer, boom, 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 many layer, and you get a predict Y. And give a label Y, ground truth, could be just a number or a class. So for example, this is fish, tiger, dog, monkey, blah, blah, blah. So this is a fish, okay? So we define loss between Y hat and Y. Loss is plugging in the complicated machine learning model. So you plug X and into machine learning. Then it will give you predict Y. If you fix the parameter, okay? So we talk about fixed parameter, we always get a Y hat. Later on, you adjust parameter, then your Y hat adjusted. That's why your loss keep on changing. But you want to catch the minimum loss guy, okay? So, and our job is to solve the parameter in the model to minimize the distance between, not distance, loss between Y hat and Y, okay?
Is there a way to guarantee, like you adjust, I mean, is there any methodology to like either adjust the parameters and it will always get a better result?
Oh, this is convergence result. Yeah.
Technically, there's no like guarantee,
No,
but
right,
it empirically works because like the gradient. If you go down the path that follows the gradient, like the steepest slope down, most likely it's going to get way better.
Yeah. So like some kind of.
Sometimes you can like
you
overshoot
can
or
chop.
something,
You
but
can
like
chop.
that's unlikely.
So sometimes it's this one. Then you're going down, down, down. You are chopping this point instead of which
Yeah,
other.
theoretically, yes, if you follow that, but
Yeah.
in the reality,
No,
if you
in
are
the reality-
training a model, I think if it just a tiny bit, and it will you will get completely different result.
Because you are not training one data, you are training by batch.
Right.
And there is a stochastic picking there. So everything together won't data.
Also, these values like generally we change the parameter values by like small amounts.
Yeah, you want learning rate very low. Like in my research, I using learning rate is negative 10 to the negative 5.
Okay.
Very low learning rate. So basically, you're
So that's
talking
just like
So
That's
the
new.
parameter actually is 0 to 1.
yeah. So this is the
I mean, not
learning rate.
necessarily. It can be like any like real value. But like, let's just say it's 0 to 1, and then we have learning rate of 10 to the negative 5. That means like we're generally changing the parameter on the order of like that magnitude, which means it's not actually changing the whole
big
thing.
thing.
Yeah.
Yeah, move a little. Look at this formula. That's the new formula. That's the old.
Okay.
That's the learning rate. That's the gradient, partial derivative. So you multiply partial derivative by 10 to the negative 5. So usually It's very magnitude.
But that will need a lot of iteration.
Yeah, a lot of
to
it.
find
Yeah,
the
exactly.
best
Yeah.
spot, sweet spot.
Yeah.
Exactly. So that's depend on hardware. So that's why the idea of machine learning is in A day. It's never be progressed until machines. Yeah. Okay, next page. Okay, now I will teach you some simple mathematics. This is also prepared for the high school student, Lafayette College student. So to motivate them to learn calculus 3. So this is dot product. I will say dot product is soul, S-O-U-L, of all machine learning. I will tell you why it's the soul of all machine learning. You may say, what is dot product? This is a vector. I told you vector just like a list of numbers. And that's a vector. So you calculate dot product, very easy. Coordinate-wise multiply them. Okay, coordinate-wise multiply them. Then adding together. Then you summarize it 1. And you say, okay, what's the meaning of 1? I will interpret to you later. Okay, what's the meaning of 1? So then another concept is the length of vector. So if I draw a vector, it's long, it's short, I want to measure the length. Actually, it's each coordinate square sum is the length, okay? These are two concepts important. One is dot product, the other is magnitude. Next slide. Give you one example why dot product is so important. Remember, we tossed all English words into space, right? How do we measure their difference? Mom and dad, both a person, it's just gender difference. So possibly in this space, they should be very close. And remember, all vectors starting, let's just assume it's starting from origin. So what do I mean close? Really mean the angle is small. If the angle is small, they are more close to each other, right? Of course, their magnitude could be different. So there is angle. Dot product can use to calculate the angle very quickly. You just dot them, divided by magnitude. That's the cosine of the angle. Anybody, if you learn the pre-calculus now, you arc cosine, you can quickly solve the angle. So if you give the arbitrary two vector, you can quickly find their angle by this operation. And this is taught in calculus 3 course. And machine learning based on all dot product. Okay, next slide. Okay, so
you can finish the slide yet.
yeah. So if you didn't catch anything from my talk today, go out of the room, encourage your kids to learn mathematics. You said dot product is so important, which one is catch 3, okay? So that's why I told students, you never regret to be a math major as undergraduate. Possibly some of you should think very carefully to pursue a PhD in mathematics. So if a student wants to pursue a math major as undergraduate, go ahead. No matter what change, it's so useful, okay? But pursue a PhD, I would say, wait a second. You know, the job market is so terrible unless you truly like it. Otherwise, it's very hard. But undergraduate is so different, okay? Oh, when the next 4 days I will present this in Lafayette College, I will omit the PhD part because I don't want to offensive to other that part will be there. But anyway, encourage people to be math major, okay, your kids. So I will discuss 3 famous deep learning models. One is called NLP, the other is CNN, and the last one is transformer. So this is called multilinear perceptron. In the old days, when people talk about neural network, people really mean this. Okay, then eventually second generation, third generation. So how does that work? This possibly is so small, I cannot let you see. This is a patient A, heart rate. Patient A's blood pressure. Patient A's urine test. It could be more than one number, but let's just wave hands, say one number. Patient A's blood test, okay? These are 4 symbols, so it's a vector. Right, for patient A, it has numerical 4 number. Then you go to machine learning model, all this a dot product, okay? So indeed, if you learn linear algebra, strictly speaking, it's not dot product, it's matrix multiply vector. But what is matrix multiply vector? It's dot product. Matrix multiply vector, basically every row of the matrix dot product the vector. So it's the dot product, okay? So these are dot product. These are called weight. Weight are the parameter. Look, how many weight? If I have 4 input, 6 output, 4 times 6, it's all lines connected. It's called dense. So you have 24 weights, okay? Then here, 6 to 8, it's 48 weights. There's 8 to 3, another 24 weights, okay? These are all parameter. then you need to adjust. Remember, not only, if we do all linear, then we don't need so many layers. It's will collapse in one layer enough. So after linear, we will apply our activation function. I don't want to go that detail. It's just nonlinear function. And every layer has a nonlinear function. And the last layer has a particular nonlinear function. We change all the number into probability number. Basically, what's the number probability really need to satisfy? It's all number between 0 and 1, and total sum need to be 1. Okay, so it changed to be 0.1% disease, 0.1% at risk, 0.8% healthy. So based on this patient A's neural network learning, I found this patient A is healthy. Okay, it's healthy. Okay, so you basically compare this predicted value with the true label, because I truly know patient A is healthy or not. Then I compare them using not one dot compare is useless. Using millions of patients compare, I can adjust the weight until it's predicted well for most points. Yeah, not for every, it's fair, just like linear regression. So I don't think linear regression model is just so simple illustration. Everything you think about machine learning, I always jump back to linear regression. Okay, by the way, linear regression is the introduction statistics course. It's so important. That's also Taylor mathematics is important. Okay, so this is a linear dot product. Basically, linear transformation is a dot product. Nonlinear function could be sigmoid, ReLU, JeLU, SWILU, whatever. Import represent single data points. We call it token. It could be one image. And output usually is a vector, represent a probability distribution. Yeah, probability cost is important. Okay.
So who is deciding those layers? Like,
oh, very good question. So how many layers you need?
Right.
And what's the dimension of the layer? It's decided in the initial stage. You decided, the researcher.
Okay.
The researcher decided.
So you have this budget and you can afford such layers.
Yeah,
You
yeah,
decide
yeah.
the
It's based on accuracy battled with moneyness. So, yeah. Sometimes,
I mean, it's not always money. Like
Yeah,
sometimes
sometimes-
having too much layers is just
it's
bad.
overfitting. It could be overfitting. It could be bad. But so that's why we need so many researchers to testing it, to build model. So that's the part of doing research. Okay. Yeah. Okay, for a model, yeah, that's exactly. So you always have a question, very good question. For a model, numbers of layer, the dimension of each layer is fixed. Okay, usually we give random initial value for parameter because we don't know where it is. And we start to predict. We start to use gradient descent to adjust it, using gradient descent to adjust it until the parameter, the training is done. Training is done means you already feel there is no, because until some point your gradient is almost 0. Then you have nothing to change. Because you subtract 0, you're all equal to mu, then you stop. But you could trap in bad points, but that's, you know.
Does that mean it's perfect or?
No, it's not
I mean, it's
perfect.
not going to be equal to 0. It's close to 0.
Yeah.
So it's basically
How's
hard
it
it's hard to get the perfect value, but it's close to perfect. For
Yeah, now
example.
you think it's good. You at some point.
Theoretically,
Yeah.
you cannot.
Yeah.
Yeah. Or sometimes like it's far from perfect, but there's just like, it's just too complicated.
Yes.
Yeah. Or it's just never changing anymore. So actually, there was a famous scientist, Kamin He. His result is if you just use general backward propagation, this gradient, because it's multiplication of many gradient, eventually will be multiplied 0.1 to 96 times, could be approaching to 0.
Right.
Then, so this gradient, there is an issue called gradient vanishing. If gradient vanishing,
Always.
yeah, you have nothing to change, so it stopped. Then Kamin invented a thing called a skip connection, and in Resnet, his famous paper. That one was highest citation. Okay, so he's very famous. Where is he? There? MIT, he's in MIT. So I read the news. So when you say last year he got a professorship in MIT, the news say we should congratulate MIT instead of congratulating Kamin. You know, that's a so high accomplishment. So usually people say, oh, congratulations, Kamin, he become a professor in MIT. No, it's congratulations to MIT to get Kamin to be their professor. Okay, he is the highest citation professor in MIT. So because ResNet use everywhere. Originally people stacked. So backward propagation is very smart to solve optimization. It's already very smart. But once people keep on computer advanced, adding layer, then your chain rule become larger and larger, and your product of chain rule becomes zero. Then not really zero, it's near zero. Then you have no advanced movement. Then you pretty much stuck. So then he invented the skip connection. He said, we skip color layer, adding identity function. When you look at formula, you think, oh, wow, so easy. Just skip, forget several layer, add the identity function. So what? But the integration must be so deep. He sees something really make that. On one hand side, you cannot say add a random function, and the stability will vanish. So on one hand side, you need to still get the optimal. On the other hand side, you avoid the gradient descent. So I think it's great. Okay, MLP model. So I want to go one more time to review. So look at this is number 5 in the picture. What do? They chop it. This is black-white picture. You chop it into pixel. Then you layer the pixel 1, 2, 3, 4, as a vector. Then you go through a linear layer machine, matrix multiplication or dot product. Then you go to a nonlinear layer. Then you go to second linear layer. Then you got some number, 9, 5, 3, 6, 5, 6. So there's a number, not probability. Then you go to a softmax function. Generate the probability. Now when you look at this probability, you see, oh, this number is number 5. This number is number 5. Okay, basically, every number you give, if your weight is fixed, you always have fixed outcome. But you want to overall near the truth, because you know truth, this is 5. So overall near the truth, you keep on adjusting your weight until you get your truth. So it's like statistically speaking truth, okay? Yeah. So we finish MLP. So this is MLP was so cool. This from the newest one of the class. So I will give you an example. So look, I illustrate this example in 2 dimensions, but indeed this is 768 dimension or 12,000 dimension. Red represents picture of cats. One dot is one image, okay? So there are a lot of cats, different cats, okay? Whatever cats, and a lot of dogs, okay, different dogs, okay? So your idea is, I just I grab a picture. I want to know, is it a cat or dog? You want to give a decision boundary. Imagine, this is 768 dimension, all these dots spread around. So you need a 767 dimensional surface to separate them. You don't have to separate them completely, no error. You can separate them like 90% accuracy, that's good enough. Human being may have 95%, then you're good enough. So imagine, how did you generate a 967 dimensional surface to purely separate cats and dogs? No way. But multi-layer perception gave it. Basically, passing through one layer, you're going to do transformation. Another layer, you transformation. Another layer, you transformation. Another layer, until the output. Now it's easy. Since it's binary, there are only 2 outputs. You can say greater than 0 a dog, less than 0 a cat. So you can import through a picture in. Parameter all determined. Through it, then you surely get an output dot. If it's in the positive y-axis, you say it's cat. Negative y-axis, dot. Very logical. Originally in the constructor, 767 dimensional surface. Now it become a line. Binary is a line. If you have more than 1 class, more than 2 classes, you're not line anymore, but binary is a line. So that's really easy. That's MLP. I thought this picture is very good. This is online free picture. Daniel's class picture. Daniel showed me once. Actually, even cool. It's dynamically. You see, but his teacher doesn't allow him to release that to public. This one I downloaded from public resource. That's okay. So now the second model. The second model is called CNN. CNN model majorly deal with picture. So what do? The idea is very good. So basically, we talk about magnifying glass. If we want to understand a map, we really want a magnifying glass to see locally what does it look like. Then globally, summarize. Oh, this is a map of Pennsylvania. Okay. So now next slide. Similarly, the idea, look, This yellow square is magnified glass. But we don't call it magnified glass, we call filter. And the filter value are the parameter need to be trained. So initially you give arbitrary, but later on you adjust. You adjust what? You adjust the yellow square. You adjust all this yellow square's value, okay? That's called the weight, okay? That's called the weight. So now, the purple guy is your image. So your magnified glass go in the first square and then shift. Each time what do you do? Dot product, dot product, dot product. Then you dot product, you get value here. You get value here. You can dot product them and get value here. So this is the abstract value. Then usually you flatten it, stretch into one vector, then through into MLP. So every CNN model containing pooling, containing this kind of convolution layer, and also containing MLP at the end. So it's totally make a CNN structure. It makes sense because your final answer cannot be a square matrix saying dog cat. Your final must exactly match your class number. If I have 10 animals, then my final number should have 10 black. Okay, so you need an MLP at the end. Okay, so this is CNN model. This is the net developed by Lacombe, and it has convolution, just a magnified glass part. And also have pooling. What is pooling? Sometimes the picture size is too big. I think about these 4 of them, I just average them to get one number. So this is called pooling, average pooling. So there it's going another convolution, another magnified glass, another pooling, then go dense, dense, dense. These are MLP at the end. MLP. So finally, look, how many classes they have? 10 classes. Because they do the ImageNet 10. So really have 10 classes. ImageNet 10 is how many? It's not. Oh, Suffer 10.
Yeah.
Oh,
CIFAR
10.
I don't think there's an ImageNet.
Oh, that's not ImageNet 10. That's CIFAR 10. And that is ImageNet 1000.
It's just called ImageNet.
Oh, it's just called ImageNet. Okay, sure. That's 1000 class. So this is the model designed by Lacombe. And this is the model designed by Alex. So it's based on ImageNet. ImageNet is another Chinese lady's famous work. Guess what's her name? Anybody know? So there is 2 Chinese guys contributed very much. One is He Kai-min, ResNet, and the other one is Li Feifei. Yeah. This ImageNet is Li Feifei's contribution.
ImageNet is a data set.
It's a data set.
I don't.
Yeah, AlexNet, until they have ImageNet, when AlexNet was invented. Because without ImageNet, so in machine learning, I want to emphasize the data is important. The other day I checked with a machine learning expert, and he told me, do you have good data? I said, I want to do finance research in machine learning research in finance. And he said, do you have good data? If you don't have good data, we don't even have a point to begin. So you need data. Basically, data is important.
What is that class again?
Class is just a category.
Category. So like, because there are 1,000 categories, some of them car, some of them eagle, some of them.
In that model or in that database, it's only 10 classes?
Yeah, 10 classes.
Yeah, 10 classes. So it's like I think there's like
Human, plant.
No.
I think there's like several animals and like vehicles or something.
Oh, only certain.
Yeah.
But 1,000.
1,000 is like pretty comprehensive, I think.
Yeah. Okay, next one. Okay, the last model, transformer. Okay, everybody is excited about transformer. So transformer basically is invented in 2017. Like MLP is invented pretty much we credit to Hinton, the godfather of the AI. And the CNN we pretty much credit into Lacombe, young Lacombe. And this was credited to Google team. So it's a teamwork. I don't even remember the first author name. Oh, it's here. No, I didn't put it the author name. But anyway, this picture is totally from transformer paper. So it's called attention is all you need. So what do they do? Remember, we still talk about vector. Vector, token, 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 token. You chopping English sentence into one word by the other, by the other, by the other, by the other, by the other. Okay? English word. Then what do? You go to a linear layer. Linear layer, basically MLP, basically just MLP, okay, without activation, just MLP. What's the good part of MLP? Usually you can increase dimension or decrease dimension, but most likely you want to increase dimension. So original token may have only dimension 12, like I do research, I have original 12. Then I increase to 128 dimension. So like transformer, originally GPT-2, they increase into 768 dimension, okay, just increase dimension. After increase dimension, each English word generate a query, a key, a token. So I just want to illustrate transformer in very intuitive way. I thought it's cool, okay? Assuming this is me, okay? And this is Daniel, and this is KK, right? KK. And whoever name, okay, I don't know. But anyway, we all have people. So I will pop up a question. That's called Q. And I have a key, it's my label. I said, I am Qing, or some label, okay? Or math, I'm label in math. That means I know a lot of mathematics. Daniel has his own question, has a key, CS, okay? Then, for example, somebody else, KK, you're good at
Nothing.
so we label you nothing, okay? So nothing, okay? Then we begin to, your key is nothing. I have math, he has CS, okay? Oh, I still remember you do robotics, so I will make you a robotics thing. Yeah, that's your specialty. Okay, robotic. So anyway, now, then, we are entering a room, assuming we all don't know each other, right? I have a math information, he has CS information, you have, robotic information. Then we begin to communicate each other. The idea is very natural, very beautiful. So I have my query, I pop out a question. I say, KK, I ask you, what are you good at? Then you tell me robotic. That's your key, right? But you also have value. Value is detailed information about your robotic stuff, okay? Your robotic stuff, okay? Then I decided, since I'm asking you, I may be interested in robotic, I may not. If I'm interested in robotic, my query matched with your key very well. Then I assign high weight. Then eventually I grab your value more to add to me. Because I know KK.
You get some credit from me.
Yeah, from you. Next time I have a robotic question, I could ask KK. So I grab some of your value. So some, like you have a secret sheet of important information. I say, KK, can I, take a photo? Then I grab it, okay? Then I do my query, go to Daniel's key. Daniel, I saw his label is CS. I say, oh, CS, I love even better. I say, Daniel, could you give me your secret sheet? You say yes, you will say yes. Yeah, anyway, I grab his secret sheet. Now I could summarize all together into my final result. Now, what I know not only math, I know CS, I know, robotic already. So the output is also a token, but now the token is contextualized token. So what does it mean, contextualized? It means it knows nearby. I even don't know how to spell contextualize. Yeah, contextualized token really means I'm not only carrying my own English words information, I carry nearby English words information. So every word suddenly becomes an important vector. When you think about it, it's pretty marvelous. The other day I explained this to a colleague. A colleague tell me, Qing, I still don't understand. How did you carry that many information? I tell him, think about it. I have 768 dimensions, right? One dimension I can talk about gender. Then that dimension I can differentiate me with Daniel. The other dimension I can talk about, pizza. Then I can differentiate me love pizza, you don't like pizza. So eventually my information will become very rich. I know, Qing like pizza or not, Qing is a female, Qing is teaching math, all this. So it becomes very contextualized and rich. So this becomes output. Then all this output, guess what? then you through MLP to cook it into the final how many class you want, how many you want. So MLP basically is a matrix multiplication. A matrix multiplying a vector, you always can change the dimension. So for example, originally this vector is 100 dimension. If I want to change to 10 dimension, I just need to multiply 100 times 10 matrix. Then it will become a 10-dimensional vector. So you actually will have 10 classes to, whatever. Okay, next slide. Yeah, this is the way. See, look, it. Where I get the word English word it, I feel given have nothing to do with me. So I have another person, your literature, I have no interest in Shakespeare. Assuming your specialty is Shakespeare, I have no interest at all. So I weighted you at 0.2%. I don't care about you. Then eventually, see, it was mostly relevant to Robert, because it's Robert. And it's more relevant to so it's the singular it. So now the words all connect to each other. They know it is Robert. Yeah. Okay, this is basically machine, the transformer. Okay, attention. So transformer have more than attention. Transformer also has an embedding. You need a position, taking care of position, because each English word, the position matter. I am cooking is different from cooking am I. Whatever. So there is a position encoding, and this is the communication. Basically, what I say it's a multi-head attention, and there is a add means. Coming close add, a skip connection called add. And normal is the layer normalization. Then feed forward neural network is basically MLP. Then this is MLP, maybe without activation function. I didn't check with or without, doesn't matter. And then it's add and norm. Then it's go to another transformer. You can have layers by layers of transformer. So that's eventually there. Okay?
Excuse me, how does it ensure the positional encoding?
Oh, positional encoding, usually they have sine function, cosine function to do the positional encoding. That's why the picture more like a sine wave. There are multiple ways to do position. I did see a paper called a clip paper. They actually do 2D position. They can record their 2D position. So their position, you basically just need to record the coordinate, right? The coordinate. So basically, they need to be clear. Okay, next slide. Okay, now I will go super fast. This application. Okay, see this picture. So this is the modern model, the famous one, GPT-4. Llama 3 is from Meta. This from Claude. Claude is pretty good about coding. Which company is Claude? You don't know?
No.
Anthropic.
Yeah, Anthropic. Yeah. Gemini. Which company is Gemini?
Google.
Google. What's it this one?
DeepSeek.
DeepSeek. What's this one?
X8.
Elon Musk.
Elon Musk.
Yeah.
Oh,
These are the famous one. And the vision transformer can recognize vision. Let's go this side open. So vision model, there is a leading board. You can always keep track top real-time vision model. If you want to know, if you're a researcher, you want to know which is the best vision model, you should go to this website to find the vision model. Next one. Oh, there's another big category of model I didn't discuss. It's called generative model. When you look at generative model, basically it's generation. So this is more complicated. Basically, I want to give a dog, then I keep on adding white noise, white noise, white noise until it's purely noise. Then I predict the noise using neural network to predict noise and return back to, it will not be a dog anymore, it's a random thing. It could be a dog, it could be a cat, okay? So this is generative models. Yeah. So these are few very, very beautiful models. I learned from Daniel and Yiwei's class, and they let kids, play with this model. These are the website, it's so cool. You can look at it or generate picture. So how did we get this? Ask ChatGPT. And this is state-of-art AI. I always tell you what's the best thing whatsoever. Yeah, GitHub. If you want to do research, GitHub is important. Hugging Face is also important. And how do we use AI? My statistics class, in case you don't know how to import a file, I ask students, how do you import a file into R? And you can literally ask ChatGPT. you need to prompt well. You cannot say, how do I read a file? Then it doesn't know what do you need to read. You need to say, how do I read a CSV file in R? And how do I delete observation with missing value? So they start tell you the command. So as a student, now your life becomes so easy. The ChatGPT can do for you. This is fine-tuning the model. Remember, where you have a weight, it's called pre-training model, already fixed the weight. But this fixed weight is deal with all internet news, okay? You want to solve AMY problem, math competition problem. Then you don't think that all the news on the web generate a good weight. So you want to do fine-tuning, feed this machine new data, okay? This kind of fine-tuning also basically changing weight. But it's minorly changing weight. It's not fundamentally changing weight. So then there's the fine-tuning that's also needed. Then researchers develop new model. This is one paper my nephew gave me, no, not my nephew gave, I read it together with Daniel. That comes from paper 3D swing, the one you give presentation. Yeah, that's current.
That's CT image.
Yeah, CT image and MRI. And key insight, machine learning is fundamentally based on probability model. When probability model are well optimized, they often surpass human performance. However, high probability doesn't mean absolute truth. In both machine learning and real life, we often confuse high probable events with absolute truth. And understanding the difference between probability and truth is crucial. The future, you can implement the algorithm, you can create more data set, you can find a gap between high probability and undeniable truth. Okay. What you get from this talk? Cool, I can learn some of the tools in mentioned, and mathematics is crucial in machine learning. And cost to learn, calculus, linear algebra, probability, statistics, optimization. There is a long way to go. That's it.